Not all Euler's method problems are going to be worded the same way. Check this one out. Let y equals f of x be the solution to the differential equation dy dx equals 2x minus y with initial condition y of 0 equals 2. Okay, first of all, you know the slope. You know the initial condition. You keep reading, you'll find out they want us to use Euler's method. But what's all this stuff? So the solution, what do you mean the solution to the differential equation? Let's back up to the previous problem. You don't have to go through all this. I just wanted to show you something. If we were to do this, by do this, let me rephrase that. If we were to solve this for y, we could bring the dx up, and we'd have 2x. We've done this exact problem in a different set of notes, actually. We'd integrate. The integral of 1 dy would be y. The integral of 2x would be x squared. We'll put our c over here. We just found a function, so our function would be x squared plus c. And then we could plug in 0, 3. See, it's going to work. It's going to be beautiful. So we would be like f of 0 equals 0 squared plus c, and that would equal 3, so c equals 3. So our function, like final answer, would be x squared plus 3. Yay, found it. That's great. Which means that this approximation is just a little bit off, and you're probably like, well, why can't you just plug it straight in? Well, I'll tell you why not. You could have in this case, but in this case, good luck trying to get x and y on separate sides. It's not going to work, no matter what you do. So we have no choice but to use Euler's method. If I may, let me take a minute or less and demonstrate. Let's bring the dx up. So I have 2x minus y, all multiplied by dx. And then I want to get y over here, and you might say, well, add y. But no, it's attached to this. Okay, fine then. Let's do something ridiculous that looks a little bit weird and is mathematically awkward. We'll do that. We'll distribute the dx. Then we can bring the y over, so we'll have dy plus y dx equals 2x dx. And then I want to bring the dx over here, and so now what would I do? Would I divide by dx? And then if I divide by dx, I divide by dx here, and now those are gone. And then, well, those would be gone, but then I have dy over. Like, what have you done? Like, what were you thinking? You can't. You can't. You cannot separate these variables on either side. You have no choice but to use Euler's method to make an approximation given this differential equation. So what I just showed you was kind of a look ahead to some things that we'll deal with later. So if it didn't make sense, don't worry. But the beginning of this problem, which we haven't even written the first thing on yet, says let this function, y equals f of x, be that solution. And we couldn't even find it. We could find this one. We can't even find that one. So we have no choice but to approximate, and this is what we're going to do. The top of every chart is x, y, and then just a fancy way of writing m x plus b. And again, that is slope, your x, like how much you're stepping by each time, and then plus a starting point, which will be a y value. And let's just keep reading and see what we're doing. All right, f of x, the solution to that. Okay, well, I know dy dx is 2x minus y, so let's write a little bit more. So 2x minus y times delta x, don't know it yet. Initial condition is 0, 2, okay. What is the approximation for f of 1.5? Okay, 1.5, excuse me, is the final x value we're going to get to, obtained by using Euler's method with 3 steps of equal length starting at x equals 0. So again, we knew the slope, we knew initial condition, but we didn't know delta x, but we kind of do actually. We are going from, you've seen this before, we're going from 0 to 1.5. That's kind of obvious what 1.5 minus 0 is, and we're using 3 steps. So each step is 0.5. So this is step 1. Here's the beginning, step 1. Step 2, whoops, I shouldn't say 0, I should say 1.5. Step 3. So sometimes when I make my little chart, I haven't even finished writing stuff up here yet. I just realized that. Sometimes when I make my chart, I'll put a little bit of extra stuff, and I will come over here and I'll say, oh, this is what step I'm on. And so this would be step 0, this would be step 1, step 2, step 3. And if you don't want to do all that, that's fine. This does not come into play in all the calculations. That's why I made it a different color. All right, back to what's at hand here. Both hands. Slope, dy dx times delta x, that would be 0.5. consistently, and then plus y, whatever y may happen to be in any given step. So we're going to go through this. Without a calculator, my calculator is halfway across the room. No! It's going to get a little tricky, actually. Here goes. A lot of these are calculator inactive, but they're reasonable. This one might get a little tricky, but 2 times 0 minus 2, I'm looking there, times 0.5 plus y, which would be 2. So we have negative 2 times 0.5, that's negative 1. Negative 1 plus 2 is going to give me 1. Boom, bring it down. Okay? That better be right. I'm going to cry right here in this video. You won't be able to see my face. I'll draw my face over here with little tears coming down. All right, we'll plug these in. So 2 times 0.5 minus 1 times 0.5 plus 1. Oh boy, fun stuff. 1 minus 1. Oh, that's easy. 0 times 0.5, so 0 plus 1, 1. Hey, I like this. Who needs a calculator? 2 times 1 minus 1 times 0.5, and then plus 1 again. And what we're doing is just taking step by step by step by step to go from one to the next so we can predict. Again, looks like this. If I start at 0, 2, and I'm going to go up to, there's 1, there's 2, there's a half, there's 1.5, there's 1. What I'm doing is I'm starting here, and then I take a step, and then I take another, take a step, take another step, take another step, and to get where I'm going. That's what I'm really doing. You didn't need to see all that. All right, 2 minus 1 is 1. 1 times 0.5 is 0.5, and then plus 1 is 1.5. 1.5, done. We're done. So the approximation for f of 1.5 is, 1.5. When I plug in 1.5, I'll probably get something really close to 1.5. Why don't we plug it in? We can't. We tried. Couldn't even find the original function. Tragic, I know.